the wire, like this. If I'm looking at it from above, it would be counterclockwise. Okay, I'm going to do something really silly, and some of you are going to roll your eyes and think I'm dumb, but some of you, it's going to help you remember something. Because this deals in 3 dimensions, you have to be able to draw vectors that come in and out of the page. Because the paper is 2-dimensional, you can't draw 3 dimensions on it very easily. So how do you draw a vector normally? What does a vector diagram look like? An arrow, that's right. So you draw an arrow. But how do you draw an arrow on your page coming straight at you? That's not easy to do. So here's what I did. I brought with me a bow and arrow. This is where I get silly. Forgive me for being silly, but here's my bow, and I'm going to put my quiver of arrows on. Sam, you got fast reaction time, right? All right. I'm going to take aim, and I'm going to fire this arrow at you, and you're going to catch it. That was so good. I was so impressed. All right, I'm putting that down. Now don't drop my arrow. All right. Now look at it on end. It's a broadhead arrow, so you can see the head of the arrow. It makes kind of a circle, and there's a single point in the middle of that arrow where the point of the arrow is, where if you didn't catch it, it was going to go into you. Okay, that's actually how, I'm not kidding, that's literally how an arrow is drawn coming out of your page. Just like what you see, Sam. It's a dot for the point of the arrow, and a circle for the head of the arrow. That is a vector coming out of the board. If it's for me, tell them I'm busy. Now, Sam, take that arrow and flip it around. You see the fletching, the feathers on the arrow? It makes a cross, right? Like an X. But you can still, in the background, see the head of the arrow, like in the back. So you can see the circle that is the head of the arrow, but you can see the cross from the fletching of the arrow. Like that, right? And I'm not kidding, that is how an arrow is drawn as a vector arrow into the board. You can keep that if it helps you remember. This is an arrow pointing out towards you. This is an arrow pointing into the board. Why is that important? Because magnetic fields are in 3 dimensions. If I'm drawing my wire straight up like this, and I do my right-hand rule, on this side of the wire, the vector is coming out, because my fingers, they don't bend into the board, they can't. There's something really wrong with me if my right hand bends into the board there. So they only bend out of the board. So the magnetic field on this side of the wire is coming out towards you. On this, one second, I see. On this side of the wire, my fingers are bending into the board. So on this side of the wire, the magnetic field is going into the board. So on this side, it's a dot coming out, an arrow coming towards you. On that side, it's an arrow going away. Next.
So for like a diagram, we draw.
Yeah, so let's draw the magnetic field. There's a wire. This is the only part you can see. It actually goes, it continues up, it continues down, but this is the part of the wire you can see. Let's make the, that current is going up. Let's make this current going down. We have a current carrying wire with a current going down. We take our right hand, we take our thumb, point it in the direction of the current. Ava, come here for a second. Oh, okay. I catch you. Okay. Stay on that side so everyone can see. All right. Left-handed, you're making this? I didn't know you were left-handed. Okay. It works out great. Okay. All right. So my right hand is pointing down. My thumb is pointing down in the direction of the current. On that side of the wire, my fingers are curling. What direction do they curl? Into the board. So what will the vector for the electric field look like? Exactly like that. Okay, we're going to trade spots. On that side of the wire, what's going on? Well, I can't. My thumb, okay, there we go. My thumb is pointing in the direction of the current. My fingers, which way do they curl? Out. So which way will the vector be? It'll be a dot. Does that make sense? Is it possible to have 2 different ones? Yeah, because it's a circle. What about if we were to draw the electric field right here? Sorry, I said it wrong. Correct this in the video, future me. The magnetic field right here, at this spot in space, in front of the wire, what direction would it be? What direction is my finger curling? It's a circle, remember? Which way? Right here in front of it? Towards me. What about behind the board? What about back here? Which direction would that circle be pointing? that way, to your right. It's making a circle around that wire. Thank you, you did a great job. It requires 2 hands, so I need you to draw. The fact that you were left-handed, bonus. Here's my current carrying wire. Here's my magnetic field. I actually don't know what this loop is for, but it's going to do the job. Current carrying wire, here's my loop. If the current is going up, it's going to go this way around the loop. The magnetic field will be going this way. So at that spot over here on your left, my right, it's going to be pointing towards you. Here, close to you, it's going to be pointing to your right. Here, it's going to be pointing away from you towards me. Here, it's going to be pointing to my right, your left. If the current is going up, if it's going down, it's going to be going the other way around the loop. Here, it's going to be going this way. Here, it's going to be going that way. Here, it's going to be going that way. Here, it's going to be going that way. Make sense? Savvy? Questions? Thoughts? Comments?
What if the wire's going left to right?
What if the wire is going left to right? Here's my wire. It's going left to right. I'm going to draw it up on the board. I was trying to grab this piece of chalk. Yeah, there's a piece of chalk drawn on the box. I tried to grab it. It didn't work. It wouldn't be that bad if I tried to grab it once. I tried to grab it twice. Oh my God. All right, so I've got a wire. It's going left to right. Which way is the current going, left or right? The current is going right. Right hand rule. Take your thumb, point it in the direction of the current. Take my fingers, curl them. On top of the wire, which way are your fingers curling? Towards you. Everywhere up there, it's going to be going towards you. What about down here on the bottom? Sometimes you got to do a little contortionist act, but you can get there. It's going to be going away into the board.
How do you move your hand the other way?
It's going to make a circle. It makes a loop. So, come here for a second. Actually, Grace, can you also, I just need 2 people to hold this wire.
Something like that.
I want to attend Silly Goose University in the worst kind of way. Which one of you is more positive in general? All right, so the current is going to be going from positive to negative. It's going to be going this way. Current is going from Grace to Sienna. Take my thumb, point it in the direction of the current, curl my fingers. It's going to make a circle that goes in the direction my fingers curl. So on this side, it's coming up. Up here, it's going to be going towards me. It's going in a circle around the wire. Yeah, a closed loop circle. Every one of these circles goes all the way around and makes a closed loop circle. They're all concentric around the wire. If I switch the battery and it's going the other way, it's going this way, take your right hand, point your thumb in the direction of the current, curl your fingers, and it makes a circle around the wire like this. So here it's going down, here it's going towards me, here it's going up, here it's going towards you. It goes in a loop around the wire. Okay. How strong is the magnetic field? Now we know the direction. It's a vector, and direction is important. We also need a magnitude. We have to figure out how strong it is. If you want to find the strength of the magnetic field, there we go. We have an equation for that. We have an equation for that. For a current carrying wire, the magnetic field equals, for now, just write it down, save the questions. I'll explain piece by piece. Mu 0 times I divided by 2 pi r. The magnetic field vector, the direction is found through the right-hand rule, specifically the right-hand curl rule. There's going to be another one we're going to talk about today. The magnitude of it, how strong the magnetic field, equals mu 0 times I divided by 2 pi r. Mu 0, that, bless you, is nu. It is the variable mu naught, which is the permittivity of free space. No, permissibility. It's one of those two. It's either permittability or permittivity of free space. It's one of the two. Epsilon 0 was the other one. Do you remember Epsilon 0? I remember that guy. He was fun. He was a good dude. Epsilon naught. Epsilon naught was a constant that talked about how easy it was for electric fields to move through empty space. Mu 0 is like his cousin. Mu 0, I have to look up the actual name for it. I got my flub on video. Mu 0 is the same thing for magnetic fields. It's how easily a magnetic field will move through empty space. It equals, it's a constant, and it equals 4 times pi times 10 to the 7th, negative 7th. Thank you. Who got that? Oh, you rock. You rock for saying it, you rock for finding it. 4 times pi times 10 to the negative 7th.
What's the unit?
Tesla meters per amp. Mu naught is a constant. It's a numerical value. It means something, but for you, for your purposes, for the purpose of this equation, it's a number. The number equals 4 times pi times 10 to the negative 7th. And thank you for the tip. I appreciate that. I is the current. If you increase the amount of current going through the wire, you will also consequently increase the magnetic field that the wire produces. More current, more magnetic field. That should make sense to you, right? If magnetic fields are due to moving charges, increasing the current means there's more charge moving. Either more charge is moving or that charge is moving faster. Either way, you have more charges that move, you have a stronger magnetic field. Divided by 2 pi times r. 2 and pi are just numbers. 2 and pi, just numerical values. R is the radius. We're dividing by the radius, which means the farther you get from the wire, what happens to the magnetic field? It's going to go down. As R goes up, the field gets weaker. The farther from the wire you are, the weaker the field's going to be. And that kind of makes sense. If we go back to that picture from a couple slides ago, notice that these two circles are kind of close together. The density of the magnetic field lines tells you how strong they are. Those two are close together because they're close to the wire. So the magnetic field is stronger here. They get farther apart as you get farther from the wire. Make a note of that, because if I ever make you draw those, you have to draw that change in distance between them. Of course I can.
Please.
The closer together magnetic fields are, the stronger the magnetic field. So as you get farther from the wire, the farther apart the magnetic field lines are going to be. Did I do a good job saying it?
Yeah, that was incredible.
Oh, thanks.
Great job. The stronger the force is, the closer they are.
The stronger the field is. You wrote it right. Right? Yeah, you did. Good job. We haven't talked about forces yet. We're going to. Anybody need me to say anything again or to clarify or reiterate? I want to kind of prove my point, though. I want to make this be real for you. I told you that this was a magnet in the video. We talked about that being an electromagnet. You hook a charge up to a coil of wire. There's a special name for a coil of wire. It's called a solenoid. Have you ever heard that term before? If you've ever worked on cars or been around a mechanic shop, your car has a solenoid in it. There's actually probably a bunch of solenoids there somewhere, but there's one part in the car that is called a solenoid, and it's just a coil of wire, just like this. This particular solenoid, this particular coil of wire, happens to have a piece of iron in the middle of it. When I make that coil of wire, if I run a current through it, that coil of wire is going to produce a magnetic field. If it's just a straight line, you know how to deal with that, right? We can find the direction of the magnetic field using my right-hand rule. But if I coil the wire into a loop, now what's going on? Well, the current, let's say the current is coming in through this wire that's close to the wall, and it's leaving through this wire that's close to that wall. It's going to be going this way around the loop. So I take my right hand, curl it, curl it. In the middle of the loop, my fingers curl towards that way, towards that wall over there. Here on the right-hand side, still curling that way. Here on the bottom, still curling that way. Here over here on this side, still curling that way. Up on top, still curling that way. Everywhere in the loop, the magnetic field due to that wire is always in the middle of the loop, pointing in this direction. If I happen to loop it more tightly and do another loop, the same pattern. If I loop it again and make another loop, same pattern. Every one of those loops is going to be producing a magnetic field, and it's always in the middle of the loop going to be pointing in the same direction. That's going to cause this iron bar to become magnetized as well. Remember what I did with the paper clips? They have iron in them. I put them next to a strong magnet. They became magnetized. They became magnetized by the magnetic field of that strong magnet. This coil is producing a magnetic field that is causing the iron in the middle to become magnetized. I actually brought one. It's a steel nail. And I just did it before class. Emily helped me find the wire, and I found the nail in the back room. I just took a piece of copper wire, wrapped it around, made a solenoid for myself, put a piece of iron in the middle, and I'm going to connect the battery to it. And we're running a current through it. And if I did it right, I should be able to make it pick up these paper clips. Now, I didn't bring a super powerful battery, just 4.5 volt set of AA's, but I'm going to connect them to my electromagnet that I'm trying to make, and we'll see if we can pick up at least one of these paper clips. If I do, will you believe me that it works? Okay, good. Well, probably. You'll see it with your own eyes. If it doesn't work, then maybe you don't believe me. I really hope it works. All right, so now we have a current going through the wire. Oh, buddy. Look at that. I made an electromagnet. It wasn't magnetic before. I take the current off, it stops sticking. No current, no magnet. Get the current going. And now we got a magnet. No, there it goes. I did actually pick that paper clip because that's the smallest one, so it's the lightest one, so I picked that one first. So these ones are a little heavier, but it's still picking it up.
This thinks it has glue on it.
They all have glue?
No, the small one has glue.
Well, then why isn't it sticking when it's not connected?
Because you're choosing the part that doesn't glue on it. You're scooping it.
That, if I was clever enough, that would be a good trick, but I can't. I'm not that clever. Here, you can have it. There's no glue on it. Way to dodge. I threw it to you. You dodged. I actually do want that back. Actually, can I have that back? No, because it's the latest one. I kept only the heavy ones. I have points to make in the next class. That's how electric magnets work all over our society, I guess. We use them to pick up all kinds of crazy stuff. Electromagnets are very handy to have around because they're controllable. Naturally occurring magnets, you can't really turn on and off. Electromagnets, you turn the current on, you got a magnet. You turn the current off, you don't have a magnet anymore. So you want to... metal detectors use something else. They use electromagnetic induction, and we will talk about that. They actually do use a closed loop of metal. That's why you have to walk through the gate. It's kind of neat. You're inducing a magnetic electric field. You're inducing an electric field by changing a magnetic field. That's pretty cool. Questions about what we've talked about so far? Because we're about to shift gears and start talking about forces. Yeah?
Why really do you need to know the direction of the magnet?
Great question. Fields cause forces, and forces depend on the direction of the field. The next right-hand rule, we'll need to know the direction of the field to figure out the direction of a force acting on a moving charge. the question was, why is it important to know the direction of the field? It's pretty obvious with electric fields, because the direction of the field is the direction of the force for a positive charge. For this, it's 90 degrees, it's perpendicular. But we still need to know the direction of the field if we're going to find the direction of the force. To do that, though, we have to use the second right-hand rule, which is the next thing we're going to talk about. I'm going to introduce it today. We're going to do problems with it next class. Oh, for a solenoid, I just mentioned this, but for a solenoid, for a coil of wire, the strength of the field in the middle is N, which is the number of coils, mu naught times I. What is what?
What's N?
The number of coils. Your book gives two equations. One is capital N, which is the coils per unit length, and then this is just the number of coils. I don't like the order of events here. We're going to go to this. I'm going to come back to that last one. If you want to find, so this goes to your question a second ago, why that matters. Magnets apply forces to other magnetic fields. If this wasn't magnetic, it wouldn't affect the other things at all. But since they're both magnetic, since they both have magnetic fields, they feel an attractive or a repulsive force. The only reason that they feel that attractive or repulsive force is because they have magnetic fields of their own. If they didn't produce a magnetic field, they wouldn't feel any kind of effect. So a stationary charge does not produce a magnetic field. Only moving charges produce magnetic fields. If I pull out a proton and I just hold it here next to my magnet and it's just stationary, it's not moving, and I let it go, nothing's going to happen. The magnet doesn't affect it at all because a stationary charge doesn't make a magnetic field, so the magnetic fields around it don't affect it. But as soon as it starts to move, what do you know about moving charges? Moving charges produce magnetic fields. Thank you, that's right. Moving charges make magnetic fields. So as soon as I take that charge and I try to move it, it's going to feel a force. The amount of force that charge will feel depends on how much charge it has, how fast it's moving, the strength of the magnetic field, and the angle between the velocity and the field. Again, it's a cross product, that's why the sine theta is in there, but it is important. Jot it down, we're going to cover it in more depth next time. The direction of that force, this is what we're going to pick up with when we do the problems, because I'm going to make you do a whole bunch of these. The direction of that force is found through the second right-hand rule. I call this one the right-hand push rule. You can call it whatever you want. You call it the second right-hand rule. You could call it Sienna if you want to. I don't care. Take your right hand. You point your fingers in the direction of the B field vector, the magnetic field. You take your thumb and point it in the direction of the moving charge, in the direction of the velocity. You take your palm, and whatever way your palm would push, that's the direction the force is going to feel. We are in a magnetic field right now. The planet Earth is a big magnet. It has a general magnetic field pointing north. North is towards the front of the room. It's actually towards the front right of the room. We're going to call it right to the front of the room. If I take my proton out of my pocket and I throw it to you, I'm going to throw you this proton. The proton velocity is that way. The magnetic field is that way. What direction will the force be? Take your right hand. The magnetic field is pointing to the front of the room. So take your fingers to the front of the room. Take your thumb, point it towards the direction of the velocity. I'm going to, there. The magnetic field's pointing this way. I'm throwing it to her, so it's going that way. So what way does your hand push? Down. So if I throw it straight at your face, you better aim 5-hole. Go low. Right? Oh, good. You caught it. Now, she's going to throw it back to me. She's going to throw it back to me. The field is still to the front of the room, but the velocity is going to be pointing this way. What direction is it going to go? Got it. All right, I'm gonna go upstairs into the chemistry department and drill a hole in the floor. And I'm gonna drop my proton straight down. Drop it right through the hole in the floor. Magnetic field still to the front of the room. Velocity is down this time. Which direction is it gonna go? It's gonna feel a force that way. She tries to throw it back up. Magnetic field still at the front of the room. Force is gonna be that way. We're gonna do some practice problems with this next time. I'm going to push the quiz to the following Monday. It was all right. It was really warm for the first week, so I was outside a lot. A lot of Joey time. That's the important part. Yeah. He was in school, but that's okay. I get to do the dad stuff I don't normally get to do. His mom was out of town, which makes it even better. It was just him and me. And it was cold over the weekend, and I didn't get to do as much, and it's always sad to say goodbye. And coming back, my plane got delayed in Denver, so I didn't get back to Buffalo until 2 in the morning on Monday. So I ended up, it was too late, so I just crashed at a friend's house because I had to be here for an 8 a.m. lab to teach. So I had 2.5 hours of sleep, but I slept last night. So, made up for it. But all in all, I would say a successful trip. I was pretty happy. How about you? Was your spring break good?
Yeah, it's very good.
Did you have any games or anything? Is it good training?
Yes.
Good.
It was just a lot of conditioning.
Okay.
Not very good training.
It's such a weird order of events for you guys. Like, you're playing really hard games and then you do your training?
Yeah. We have 3 hours a weekend.
Yeah.
It's in Grove City.
Oh.
They're like,
Compared to who you've been playing?
yeah. So it'll be good. There when I went to bed.
Well, welcome back. I'm glad everybody's back safe. Oh, attendance sheet. Attendance sheet. Thanks for the reminder. Kara, I haven't done any electric demos out of your concern, but I'm going to do one today. So if you need to step out during that, go ahead. All right. So, did everybody watch the video? Was everything clear in the video? I'm glad you said that because
Can you turn the second left? Because I don't know where to do that. I never done the keys or anything, I swear. Yeah, I just swear.
don't swear in my class.
I promise I'll do it.
There's still a football Friday.
We'll see how far we get today.
Is that just going to be on?
Yeah. You guys have so little faith in me.
When have we even done?
Well, most of you guys watch the video. What?
For tomorrow.
If we have time, yeah. I didn't bring it with me, and I got a couple things to do. But I've had a couple requests. Also, I'm going to do it during office hours too. So 1 to 3. That gives us more time to practice with it too. Instead of me just talking and showing, we can have you actually do it. Yeah, so 1 to 3, a couple people are coming in to do multimeter stuff. If that's something you're interested in, come on in. I did bring with me something kind of cool. We're going to start with just a cool demo that I wanted to do before, but we just didn't have time. So we ended up skipping it. But I don't like skipping my demos. It's like my favorite part of my job. So I brought it today to play with. It's a Tesla coil named after Nikola Tesla. Part of the reason I'm putting it in today is we're talking about magnetic fields, and the unit for magnetic fields is the Tesla, named after that same guy. This is kind of neat. It generates a really, really high voltage. And if the voltage is high enough, it can overcome even the resistive properties of air, and we can send little, usually about an inch long little bolts of lightning out of it, which is pretty neat. No problem. The Tesla coil was actually invented as a wireless way to power things, and I'll show you how the electric field generated by this can actually light up a light bulb, which is kind of neat too. After that, we are going to talk about the right-hand rule. Sam, you brought it up. I'm glad you did, because that's the first thing that we're going to be talking about. Because it's pretty important to think about how electric fields and magnetic fields interact with each other. This thing's generating a really strong electric field. We've learned about electric fields. As we're learning about magnetic fields, Magnetic fields come from moving charges. Magnetic fields come from changing electric fields. So we're going to hopefully make that connection today. And we'll see how far we get. If possible, we're also going to talk about the forces that electric charges feel due to magnets. And that's definitely all the time we'll have. Sound good? All right, cool. So as I was saying, this is a Tesla coil, and if I push the button, we just found it. I don't know how old it is. It's probably older than me. It was 150 bucks whenever they bought it, though. It's still got the price tag on it. When I push this button, that was cool. It's generating a lot of electric potential, which is actually interfering with our screen. That's super cool. I didn't anticipate that being the case. I'm not going to go over the details of how it works, but that's a good question. What is the point? It's generating really high electric potential. The potential of this is much higher than the other stuff around it, so it's going to move charges in that little arc we saw as it was going to that metal towards the ground, towards a low level of potential. And if I can put something in between this thing and that low level of potential, it can actually cause that thing to get an electric current going through it. I need a volunteer who's not afraid of a zap. That was immediate. It actually, I don't think it's going to zap you, but you don't have a pacemaker, right?
I don't think so.
Okay, so all you're going to do is hold this in between my Tesla coil and the ground. Just hold it like that. Yeah, right in the middle. Everybody say a small prayer. I don't know if I've never done this, so we'll find out if it works. All right, here we go. Did it zap you?
No.
Oh, sweet. Now, can you smell the ozone?
Yeah.
You can smell ozone because every time, like lightning, in a lightning storm, you can smell ozone as it's breaking through the air. It's breaking down the chemical structure of the gases it's going through and producing ozone, which is kind of neat. It's lighting up. I'm not touching that. I don't know if you can tell because the lights went out, but I'm not touching it. I'm this far away from it and still lighting up.
Stopping where my fingers are.
It is stopping where his fingers are. Why is that? He's a conductor. He's giving the charges a path to get to the ground. Just be careful because it might actually go through you, right? So we can actually light it up with the Van de Graaff generator as well, but I didn't have a chance to bring the Van de Graaff generator over. Isn't that cool? Oh yeah, we can do it. Yeah, we can try that.
I'm so holy.
Yeah, do you mind? I can only go so far though. I'm limited by the cable. Let's see how far it'll reach. Yeah, that's pretty good. That's awesome. I didn't. Yeah, that's ozone you're smelling. Can I do it if I hold it?
Is that?
Sure. I don't have a pacemaker either. Thank you, Sam. So Tesla actually invented this as a way to light light bulbs without wires. And this was in like the 1800s, so it's pretty wild. The Tesla coil itself is wired to the wall. The light wasn't wired to anything.
Okay.
The light was freestanding. So I could have the Tesla coil in my basement, and I can have my light bulb up in the living room, and it would light up with no other input.
Is that why Tesla cars are called Tesla cars?
They're named after the same guy. Tesla was a forerunner of a proponent of AC current as opposed to DC current. This actually happened fairly locally. There's a huge amount of debate in early electronics as to what was better. So Edison, famous inventor, and with his light bulb.
That thing's worth some money.
Holy moly. Anybody want to buy it? It's only $432.
And there's 64 cents.
Well, I cut it down a little bit if you want to buy it.
Oh, wow, that's a deal.
And no shipping. If somebody walks off with that, I'll be really upset.
You didn't even know it was a thing. You just found it.
No, we found it in a closet.
Exactly. You didn't even know it was existed.
But it's awesome. Dr. Treese and I were playing with it for a while. So
You guys are gonna.
That's true. More than we already have. Okay, so as I was saying, the debate between whether electric energy in the United States should be AC or DC was huge, hotly debated, because it was a big money thing. They were making electricity in the US to light up houses and bring about sort of this modern electronic revolution. But Edison had largely invested in DC. He made DC generators, he made DC products that ran off of direct current. And it didn't benefit him to use AC because he wouldn't buy his stuff. And he wanted to sell his stuff. He was a businessman. He was a famous inventor, but mostly he was a businessman. Thank you. So he pushed DC and said that AC was inherently dangerous. The voltages were higher and it was really dangerous. People were going to be killed. As part of a propaganda campaign, he helped to invent the electric chair to show how dangerous AC power was. It would kill people. They made videos of animals getting electrocuted with AC power and put them out into the news and say, look, this is so bad. But we use AC now because it is substantially better for something called line loss, which we're going to talk about in this chapter. Transformers, the transformers, not the robots in disguise, not the movies and stuff, but the things on the electric poles outside of your house, those use AC to, and some of the concepts we're going to talk about in this chapter, to generate really high voltage but really low current. P equals I times V. If voltage goes up, current goes down, and you can get the same power transfer. High current means high energy loss in the lines. Low current, high voltage means low energy loss in the lines. So you can transport energy much farther. And a lot of this debate happened in Niagara Falls. If you ever have the chance to go to the Niagara Falls Power Vista, it's a history of, it's like a science center, but it's a history of the development of electricity. Pretty neat. So all of that's fun facts, just because it's fun to know stuff. Let's talk about the physics behind it right now. So the Tesla coil was actually using alternating magnetic fields to generate high voltages to emit electric fields through space, which lit up the light bulb. In my video, I talked about magnets, and I brought a couple magnets with me. These are hematite, magnetic hematite. Hema means iron, I think. It's a ferromagnetic material, ferro meaning iron, Fe on the periodic table, it's Latin, it means iron. Ferrous, it's the Latin word for what iron is. Iron, nickel, and cobalt are the most common naturally occurring ferromagnetic materials that are actually just naturally magnetized. I think in the olden days they called it lodestone. You can look that up. I'm not 100% sure if that's true, but I know that that's one of the names for it from somewhere. So they're just fun magnets that they stick together. I'm gonna pick that up. Pick this one up. This is a rare earth neodymium magnet. This one is way stronger. So this one, I try to pull them apart. I can pull them apart. I try to stick them together. Even if it's the wrong side, it's hard to stick them together, but I can sort of overcome the power of that magnet. It's not that strong. This one, that's not the case. I got it apart. Here. Let's see. I can move it through the desk.
Oh my god, I used to have those things.
I don't know if these ones are strong enough to do that or not. They might be. Yeah, they can. If I use this one, it can move it much better. This one, kind of slow. Awesome. I'm going to pass those around. You're going to try to pull them apart, and you're going to see that I'm not pretending. To get them apart, I have to slide them. I can't just pull them apart. They're too strong for me to pull apart.
Are you just me?
It's possible. I have to hit the gym. Professor McKenzie, did anybody ever have a class with him? Geoscience professor down the hall. He just retired last semester. His classroom is right next to my office. So I get to listen to his lectures. And he was talking about neodymium magnets and how you could use them to murder people. I'm not going to tell you that because it's not part of the lesson. And I don't want to be finding these in my food. So don't... not going to do it. Pass those around. So those are naturally occurring magnets. Why do they do what they do? All magnetic fields, this is something to jot down. Sometimes people complain that I don't tell them what to write down. I'm telling you to write this one down. All magnetic fields are due to moving charges in one way or another. The neodymium magnet, so then you can stop writing after you've written that part. Now you can just listen. The neodymium magnet, the hematite magnet, the iron magnets that you're going to use in lab next week, all of the magnets that you played with as a kid. If you're like me, I play with magnets all the time. My grandparents worked at the fire hall, and they'd bring me down to the bingo sessions at the fire hall, and I'd play with the bingo magnets. They're fun. Magnets are cool. Named after a area of Greece called Magnesia. Interesting. I found two different accounts of the history as I was prepping for my lessons. That's the one I think I believe more. I've heard that one in a couple different places. But those magnets have inside of them atoms, and those atoms have charges, and those charges move. They move in a specific pattern based on the structure of those atoms that gives them a general magnetic field pointing in one direction. Most materials, they have moving charges, but they're randomly oriented. So they have some magnetism this way and some magnetism that way. And since magnetic field is a vector, jot that down, magnetic field is a vector. Because it's a vector, if one of them's pointing this way and one of them's pointing that way, those two vectors cancel each other out, right? They add up to negate each other. So in general, most objects aren't magnetic. Some objects are called paramagnetic. That means they can be magnetized. They can become magnets, but they aren't magnets by themselves. So this is a piece of steel bent into a paperclip. Steel has iron in it. Iron can be magnetized, but it's not magnetic right now. Aluminum, it won't stick to, anybody have an aluminum can? Give me the one set of magnets, please. I'll give it back to you. If I try to steal your can with my magnet, it doesn't work. It doesn't stick at all. Nothing happens. But if I try to steal these paper clips with my magnet, I can do it. The paper clips do stick because I can magnetize them because they're iron. What happens when I do that? The magnetic field from this causes the small magnetic domains inside of this to align with this magnetic field. When they align with that magnetic field, the average magnetic field coming out of this one aligns, and it becomes magnetic itself. And it'll stay magnetic temporarily until it re-randomizes. So I can show you that because I can stick the magnet to the paperclip, and I can stick a paperclip to the paperclip. And this is another thing I used to do in my grandmother's office. She was a physics professor too. I'd see how many I could get for a given magnet. I can't get a third one. I can just get the two. If I take the magnet away, it will remain temporarily magnetized, but the magnetism goes away pretty quickly. So it wasn't strong enough to hold up 3 anymore. After a minute or two, this one will fall off as well.
Did you get more to use a stronger magnet?
Indeed, you could. Do you have the stronger magnet?
So that's.
Do you want to try? Oh, geez. It's so strong, it just pulls them up. It overcomes the gravitational force and lifts them up by themselves. So we'll try to get them a little farther away. Yeah. It did pick up all 3, but then it picked it up close enough that it just stuck to them.
Turn around. Good.
Sorry. It's not really that exciting. I'm just sticking 3 paper clips together. The magnet is so strong that when the paperclip gets magnetized, it actually lifts it up, but it does hold all 3. And you could probably get a couple more on there if I was dexterous enough. All right, that's mostly a review of last time. This is the new stuff. If moving charges create magnetic fields, I just told you all magnetic fields are due to moving charges. So moving charges make magnetic fields. We've been talking about moving charges a whole bunch, haven't we? Like all semester, we've talked about moving charges. Charges moving around. What do we call moving charges? In a circuit, we call that current. So moving charges make magnetic fields. Currents are moving charges. What does that tell you? Currents make magnetic fields. So a current carrying wire has moving charges in it. Those moving charges make magnetic fields. Currents make magnetic fields. The direction of the magnetic field generated by a current is determined using something called the right-hand rule. I'm going to do one of those things where I tell you the mistake you're going to make. And then most of you will remember because I made a point of it, but a few of you are going to forget and make this mistake. You're going to be writing, because most of you are right-handed, you're going to be W-R-I-T, writing with your right hand, and then you'll get to a right-hand rule problem, and you'll pull out the empty hand, and you'll do the right-hand rule. But which hand is that? It's your left hand. It is. I know you're going to do this because I did it. When I was sitting in the seat that you're in, I did the same thing. I had a student a couple semesters ago in Sharpie on the exam, wrote a big N-O with an exclamation point on his left hand so he wouldn't do it, because he did it so many times. I'm warning you now explicitly so that you don't make the mistake. It's very common. Dr. Tree says every single time you do one of these, you mentally you make the note, put my pencil down. Just don't forget, that's all. Okay, so you use your right hand. There are 2 right-hand rules in this chapter. That's the confusing part. The right-hand rule by itself, not that bad. The fact that there's 2 of them and they're used for related but different things, that's a problem. Also, another issue with right-hand rule stuff, everything with magnetic fields is more complicated than electric fields because it's cross products, not dot products. And if you remember from physics 1, cross products mean it's perpendicular. Because it's perpendicular, that's why we have to do the right-hand rule. With an electric field, the forces were in line with it. It was a dot product. Everything, if the electric field is going that way and I put a proton there, it's going to feel the force that way. If there's a magnetic field in this room and I have a proton just sitting there, nothing happens to it. Only when charges are moving do they create magnetic fields, and only when they create magnetic fields are they affected by outside magnetic fields. So now if I took that proton and I threw it and somebody caught it, then it's affected by the magnetic field. But the crazy part is it's affected perpendicular to the direction of the field. If the field is pointing this way, it's going to feel a force either up or down, not side to side. Does that make sense to you? Not in the direction of the field, but perpendicular to the field, and also perpendicular to the direction of its travel. So we have to think in 3 dimensions, another level of confusion. My promise to you is still valid though. First day of class I said, yeah, this stuff is hard. I'm going to make it as easy as I can. But you got to meet me halfway because it's not easy. It is confusing. I'm going to do my best, as long as you do your best too. All right, the first right-hand rule, sometimes called the right-hand curl rule because it involves you curling your fingers. I take my thumb and I point it in the direction of the moving charge. So in this case, I'm going to go to the next slide. In this case, I have a current carrying wire going up. So let's say I have a wire, and that wire is strung from the floor up to the ceiling of this room. And there's a current going from the floor to the ceiling. I take my thumb and I point it in the direction of the flowing current. It's flowing up. My fingers only bend one direction on my right hand. They only bend this way. That direction is the direction of the magnetic field. Write this down, this is important. Magnetic fields curl. C-U-R-L, curl, not the Canadian sport curling. It is, but it's not the same thing. Homophone, not homonym, not the same thing. They don't mean the same thing. They're different words. It just means they go in a circle. So after you write down magnetic fields curl, write this down. No, you got it right. C-U-R-L.
Yeah, I corrected it. It was A-L. I don't know what's going on. Anyways.
All right. After you write down magnetic fields curl, you're going to write this. They always form closed loops. Curl is actually a mathematical term, believe it or not. It has to do with vector derivatives, but this isn't a calc-based class, so we're not going to really get into that. It is important to note that what it means is they're forming closed loops all the time. Do you see these red lines on this picture right here? Those red lines are the magnetic fields generated by that current carrying wire. You take your thumb, you point it in the direction of the current, it's going to make a circle, a closed loop that goes around